Welcome back. Today we're going to work with scientific notation. And scientific notation is a natural extension from working with our laws of exponents, because we will use the laws of exponents on base 10, and it will allow us to work more easily with very large and very small numbers. Scientific notation is used quite a bit in chemistry and physics, and scientists throughout the world use scientific notation. The format of scientific notation is A, or some integer, and not necessarily some integer, but some number, times 10 to the nth power. And the nth power, that must be an integer. But the A, or the absolute value of A, is some number between 1 and 10. It can be exactly 1, but it can't be 10. You know, that 9.9999999. And A can be both positive and negative. So to begin, which of the following are written in scientific notation? 0.865 times 10 to the 5th. Well, it sure looks like scientific notation, but because the A value is less than 1, that number is really not in scientific notation. If we were to correctly write this in scientific notation, we would have the value 8.65 times, I believe, 10 to the 4th power. What about the second one? 78.96 times 10 to the 8th. Well, my exponent's an integer, that's good. But 78.96, my A is much greater than 10, so that's not correct. We need to rewrite that. 7.896 times 10 to the 9th power. 5 times 10 to the negative 3rd. Well, I've got a negative exponent. That's okay. We can have a negative exponent. That integer is fine. I have 5. That's between 1 and 10. So yes, that one is okay. That is in scientific notation. And our final example here, 10 to the 25th power. I have negative 4.006 times 10 to the 25th. I have an exponent that's an integer, so that is fine. I have a negative number here, negative 4.006. I've got, this is between 1 and 10, but it's negative. Well, that's okay, because it's the absolute value of A. So that is fine. That is in scientific notation. If I were to write this out, this would be 4006, and it would be followed by 21 more zeros. Oh, no, 22 more zeros. Okay, so that is a very large number. While our 5 times 10 to the negative 3rd, that has a negative exponent, that actually is a small number. That's 0.005. That's pretty small. That's getting closer to 0. And that leads us to my helpful hint here with scientific notation. In general, numbers with positive exponents, okay, the 8, the 25, are larger numbers, while negative exponents, not necessarily negative numbers, but negative exponents, are smaller numbers or closer to 0, like this 0.005. Well, let's work on some samples in scientific notation. Let's take this number, 29,800,000, and rewrite that in scientific notation. Well, that's a large number, so I'm going to have a positive exponent on that. And I'm going to move my decimal place 3, 6, 7 places. So I'm going to move that 7 places. So that would really be 2.98 times 10 to the 7th power. Whereas this particular one is a small number, so I can anticipate having a negative exponent. And I'm going to move my decimal place 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decimal places. So I have to get 5.03 times 10 to the negative 10th power. So that is a small number, so that's going to have a negative exponent. So in A and B, we converted from standard notation to scientific notation. Now we're going to go in the opposite direction. We're going to write 2.51 times 10 to the third in standard notation. I have a positive exponent, so that's going to be a larger number. I know that's going to be a little bit larger. So I'm going to move my decimal place to the right 3 places, 2, 5, 1, 0. And that is 2.51 times 10 to the third is simply 2,510. In sample number 2, I've got a negative exponent here, so I know this is going to be a smaller number. I'm going to move my decimal place to the left. It's fine that this is negative, so I have a negative, and I'm going to move it 4 places to the left. So 0 point, I'm going to have 3 zeros, 6, 8. And let's check. 1, 2, 3, 4. That is correct. 4 decimal places. So negative 0.0068 is that in that decimal form or standard notation. Let's take a look at a different kind of problem that you'll see in your exercises here. A little bit higher level application of scientific notation. We want to simplify this number. We want to write this in our answer in scientific notation, but we want to do this without using a calculator. So the first thing we want to do is we want to rewrite all the factors into scientific notation. So 200,000, well, that is going to be 2 times 10 to the 3, 4 to the 5th power. So we have 2 times 10 to the 5th for the 200,000. 0.003, that is a small number. So we're going to go times 3 times 10 to the 1, 2, 3, 4 decimal places. I move this 4 decimal places to the right. So that's times 10 to the negative 4th. And then finally, let's rewrite 6 100ths. That also is a small number. I'm going to move my decimal place 2 places to the right. And I'm going to have 6 times 10 to the negative 2nd. So that's a small number. That makes sense. I have a negative exponent here. So I've rewritten all of this into scientific notation. Now the second thing I want to do is I want to collect all my integers and simplify. So I'm going to rewrite this using the commutative property. My integers are 2 times 3 all divided by 6. And then I have all of my laws of exponents here. So I've got 10 to the 5th in the numerator and 10 to the negative 4th in the numerator, all over 10 to the negative 2nd in the denominator. So I've rewritten that. And I can simplify 2 times 3 divided by 6, that's just 1, times all of this. Well, I can apply my laws of exponents here. So I'll bring down my 1, and now I will go ahead and apply my laws of exponents. I have the same base. I'm working with base 10. So all 3 of these are base 10. And I have a power times a power in the numerator, so I will add those. 10 to the 5th, plus, you plus and minus guys will love this, plus a minus 4, plus, well, this is not plus. We're in the 10 to the negative second in the denominator. That one we're going to subtract that one. So that's minus a minus 2. So we end up with 1 times 10 to the 5 minus 4 plus 2, which results in 1 times 10 to the third power. And that's my answer in scientific notation. Okay? Or it's also 1,000. So scientific notation is 1 times 10 to the third power. If I just wanted it in standard notation, that would be just the answer would be 1,000. And finally, a word problem. Might have a couple of word problems. We'll see somewhat of an application of the laws of exponents. The distance to the sun is 9.6 times 10 to the 7th miles. How long would it take a satellite traveling at 3.2 times 10 to the third miles per hour to reach the sun? And let's assume that the satellite does not burn up prior to reaching its destination. So this is in miles. So if we take our distance and divide it by our rate, we can find our time. Don't we know that rate times time equals distance? So we have a distance and we have a rate. So our time equals distance divided by rate. So our distance, 9.6 times 10 to the 7th, all over 3.2 times 10 to the third. And we can use our skills from the previous problem. We can simplify our integers. 9.6 divided by 3.2. That's simply 3 over 1, or 3. And then times, applying our laws of exponents, we have a positive 3 in the denominator. We subtract. So that'd be 10 to the 7th minus 3, or 3 times 10 to the 4th power. And that is our rate in scientific notation, or it looks like that would be 30,000 hours. That seems like a long time. So that is the answer to our question. That wraps up the introduction on scientific notation, and we will see you in class.